I put this straw in here, we get this weird optical illusion where the straw kind of looks like it's kind of split or broken, right? Now this is happening because light travels a lot slower through water than it does through the air. So refraction is the effect of the light moving through the different mediums at different speeds. And the measure of each material's ability to bend the wave, in this case light, is called the index of refraction. And what this index measures is basically how much does the light in the material bend in relation to this normal or perpendicular line to the material boundary. So this line here is making a 90-degree angle to the boundary. The index of refraction tells us how much that light is going to bend as we turn this lens. You see that if I turn it, it is slowly bending toward that normal or perpendicular line to the boundary. And the higher the index of refraction, the more of this bending occurs. This has a very simple equation to go along with it. Our index of refraction, n, is equal to the velocity of light in a vacuum, which is a constant, c, divided by the velocity of that same light ray in the material. So this ratio is known as the index of refraction. And it tells us how much this light bends as it passes through the material. We have what is called a plano-convex lens. Called plano-convex because one side is a plane and the other side is a convex shape. Now let's notice what effect this is having on our light. Notice that we have a plane of lights shown by these three parallel rays hitting this plane where the lens begins. It goes through the material and of course refracts and gives us this result of concentrating the light at a single point in space right there. And this is called our focal point. And we can measure the distance to the focal point by measuring where the lens curvature begins, which is right here, to where that focal point is. And in this case, we bring that right down, it's about 6 centimeters. So the focal length of this specific lens is about 6 centimeters. The focal length tells us how powerful a lens is. So the measure of this ability to refract the light is called power. And power is just the reciprocal of the focal length, so it's just 1 over f. The further away this focal length is from the lens, the further away this point is, the lower the power we have. And conversely, if the focal length is smaller, if this point is closer to our lens, that means we have a more powerful lens. So in this case, our power would be equal to 1 over 6 centimeters, but we have to convert that to meters. So it would be 1 over 0.06, which would give us 16.66, and the unit of measure is diopters. So if you're like me and you need eyeglasses to be able to see out in the world, then you're very familiar with this, because this more or less is what your optometrist is working with. They are managing different lenses with different focal lengths such that it focuses the light on the right place in your eye. Now, because this lens takes rays of light and converges them onto a single focal point, this lens is also called a converging lens. And because when the focal length is downstream from the source, So the light is here, our focal length is on the other side of that lens. That makes our focal length positive. And this lens is therefore also called a positive lens. And one more thing I want you to notice is that, what do you think is going to happen if I flip this around? Think about what you think is going to happen to that light on this side. Guess what? We still have the same exact effect. The focal length is unchanged. The focal point is in the same spot. And this is because the focal length, the power of a lens, is completely determined by the material and by the curvature of that lens. Now let's bring another lens into the mix, and this is called a plano-concave lens. Again, one of the sides is a plane and the other is a concave shape, thus the name. So how do we measure the focal point of this one, right? Because this is really not focusing anything. It's taking that incident light and it's actually spreading it out. And for that very reason, this lens is also called a diverging lens. Let's come back to the question of where is the focus and what is the focal length of this lens. Now, this obviously isn't focusing light on this side. We could have an idea of what the focal point is if we think that if we were to trace these rays back to the left side of this lens, they would at some point focus into a single point. So if I trace this out, this would be our focal point for this lens. And we can then measure the focal length using the same procedure, 4 centimeters. But since the focal point is upstream from the lens, it happens before the lens, this is a negative focal length. And the associated power, which is just a reciprocal of the focal length, would also be negative. So this would have a power of negative 25 diopters. Now lastly, because the focal length is negative in this case, this is also called a negative lens. And once again, let's put this to the test. Does changing the orientation change where the focal point is? We can see that the focal length and the focal point really remain the same, regardless of the orientation.